this video, we will cover the polar non-return to zero scheme. Unlike unipolar scheme, signal in polar scheme encompasses both the positive and negative sides of the time axis. NRZ-Level and NRZ-Inversion are the two variations of polar non-return to zero scheme. In non-return to zero level, also abbreviated as NRZ-L, level of voltage determines the value of bit. For bit 1, we take negative voltage, and for bit 0, we take positive voltage. Let us look at an example. Consider the data 0, 1, 0, 0, 1, 1, 1, 0. Here, the first bit is 0. According to the rule, bit 0 is represented by positive voltage. So we draw a straight line at positive level. Next, we have bit 1, which is to be represented by negative voltage. Hence, for bit 1, we draw a straight line at negative level. Next bit is 0, so we draw a straight line at positive level. Again, for bit 0, we draw a line at positive level. Next is 1, so we draw a line at negative level. We have bit 1 again, and hence we draw the line at negative level. Again, for bit 1, we draw at negative level. And finally, for bit 0, we draw at positive level. Now, if we connect these lines, we have our signal in polar NRZ-L scheme. Now, in case of non-return to zero inversion, also abbreviated as NRZ-I, change or lack of change in voltage level determines the value of bit. For bit 1, there will be a change in the voltage level, and for bit 0, there won't be any change in voltage level. Let us look at an example. We consider the same data as before and assume that the signal was at positive level before time 0. Now for bit 0, we know that there won't be any change in the signal level, hence the signal will continue at positive level. Next, for bit 1, there has to be a change in the signal level. Since the current level is at positive, we will now draw the signal at negative. Next bit is 0, which means no change, and hence we continue at negative level. Again we have bit 0 and we continue at negative level. Next bit is 1, so now we move from negative to positive. Next bit is 1, so we have to change the level again, and hence we now draw the signal at negative. Again we have 1, and so we change the level and go from negative to positive. Finally, we have bit 0, meaning there won't be any change in the signal level, and hence we continue the signal at positive. Now, let us calculate the ratio R for the two schemes. We know that R is calculated as data element by signal element. In unit duration, we see that there is one data element, that is one bit, which is carried by one signal element. Hence, the value of R for polar NRZ is 1. Now, let us calculate the signal rate, which is C into N into 1 by R, where N is the data rate and C is the case factor. For average case, the value of C is half, and we have seen that the value of R is 1. Therefore, average signal rate is N by 2. Now let us compare NRZ-L and NRZ-I against the standard properties, baseline wandering, synchronization, effect of change in polarity, and DC component. Although baseline wandering is a problem for both variations, it is twice as severe in NRZ-L. If there is a long sequence of zeros or ones in NRZ-L, we get a flat line which causes the average signal power to become skewed. In NRZ-I, this problem occurs only for a long sequence of zeros. The synchronization problem also exists in both schemes. Again, this problem is more severe in NRZ-L than in NRZ-I. While a long sequence of zeros can cause a problem in both schemes, a long sequence of ones affect only NRZ-L. Another problem with NRZ-L occurs when there is a sudden change of polarity in the system. If the polarity of the system changes, the signal is inverted. As a result, all zeros are interpreted as 1 and all ones are interpreted as zeros. However, NRZ-I does not have this problem because in NRZ-I, bit value is not determined by voltage level. In both variations, there are DC components that carry a high level of energy. Please leave your feedback and suggestion in the comments below. Bye-bye.